All right, guys, so we are going to continue with the polynomials and kind of move on from just graphing and stating properties and whatnot. We're going to move into solving equations, finding zero. So one method to try first, as was with quadratics, is the method of factoring. So I want to go over a couple examples like that. This was a little warm-up that I used here. This is actually a multiplication, just distributing, but it's going to lead to a couple things we can use with factoring. So take a second and let's see if we can get these multiplied out, make sure we know how to do this, and then we will, like I said, use the result for something. Okay, so go ahead and pause the video, try these two out, and we'll take a look. All right, so for the first one, again, we're just going to distribute everything in the first term, or first set of parentheses, I should say, needs to get multiplied by everything in the next set. So the a times a squared is a cubed, plus the a times ab is going to be a squared b. And then the a times b squared is ab squared. And then we move on and we would distribute the minus b to everything. So minus b times a squared minus a squared b. I'm just going to write them in alphabetical order. Minus a b squared. And then minus b to the third power. Okay, and like usual, when we combine like terms and everything like that, we want to see what can we, or when we multiply, I should say, we want to combine like terms and simplify a little bit. So I do see a plus a squared b and a minus a squared b will cancel each other out. And likewise, there's a plus ab squared and a minus ab squared. So really, we are only left with here a cubed minus b cubed. Okay, so that whole multiplication problem just kind of simplifies down to a cubed minus b cubed. Okay, so keep that in mind. And let's also take a second and try and do the second one here as well. All right, so I went ahead and did the distributing on the first couple steps, and now let's just combine any like terms and clean things up. So similarly, there's a minus a squared b and a plus a squared b. Those cancel out. A plus ab squared and a minus ab squared cancel out. And this one is left with just a cubed plus b cubed. Okay, so what's going to happen here is we're actually going to use the result kind of backwards. If you remember how factoring is actually kind of undoing things, turning a polynomial into factors. So what that really means is like if you got something that looked like a cubed plus b cubed, the factors of it would be these two here. Okay, it's kind of undoing the multiplication. That's what factoring is all about. And similarly, if you have something of the form a to the third minus b to the third, that can be factored into these factors here. It's kind of similar to when we did, if you recall, with quadratics back in the day, we said something like x squared minus 9, for example, could be factored, right? It was the difference of perfect squares, x plus 3, x minus 3. Okay, so the rule was a squared minus b squared equaled a plus b times a minus b, right? And that was kind of something that works for perfect squares, the difference of perfect squares. What we just did here, the new part is these are for the difference of perfect cubes. There's a formula for it, or also the sum of perfect cubes. Okay, so with squares, there was no rule for the sum of squares. It was only the difference. But with cubes, there are. Okay, so let's take a look how we can use this and do a couple examples. Okay, so first off, up top there in the green is the two formulas. As you can see, it's just kind of the opposite of what we did in the warm-up. In the warm-up, I had you guys multiply the stuff on the right side of the equation, and we got the stuff on the left. And the same one below, the a cubed minus b cubed. So for an example of what we can do with it, if we had to factor something like x cubed plus 27, okay, it doesn't really obviously look factorable, but it is of the form something cubed plus something cubed because x cubed is clearly x cubed. And the key is that 27 can be written as 3 cubed. Okay, 3 to the third power is 27. So with these problems, you're going to kind of need to know some of the perfect cubes. So let's make a little list here so you know what numbers to look out for. 1 cubed, of course, is 1. 2 cubed, right? 2 times 2 times 2 is 8. 3 cubed, 3 times 3 times 3, we just saw that one in the example we're about to do, is 27. Okay, 4 cubed, 4 times 4 times 4 will be 64. 5 cubed, 5 times 5 times 5, 125. Okay, and as they get higher than that, sometimes you just got to try. You don't need to memorize like a million of these, but those first 4 or 5, you should probably be familiar. And if you see them in a problem, that should kind of jump out to you that, yeah, it is something cubed. But anyways, let's see what we can do with it. Okay, how do we factor it? So we have x cubed plus 27. We wrote it in the form a cubed plus b cubed. Okay, so really it's a problem like this. So what we're going to do is write it out and factor it following that format over there. Okay, where for our example, the x is the a, and 3 is going to go where the b's are. Okay, and this is going to be a cubed plus b cubed. Okay, the formula says, so I'm looking up here now, it equals the a plus b. Okay, so a plus b, a is x, b is 3. Okay, and now I'm just going to put in a squared minus a times b plus b squared. So the a again is x, so x squared. It's minus the a times b is 3 times x. And then the b squared is 3 squared, which is plus 9. Okay, and that's it. That is factored now. This is the factored version of x cubed plus 27. Okay, and of course you could check it if you want to just make sure you didn't make any little mistakes or anything. It is definitely, checkable, if that's a word. We can multiply out our answer just like we did in the warm-up and verify that it works. Okay, let's set up one more example down here, a little messier one. We have 27x cubed minus 125. So again, just looking right off the bat, I don't know that it looks clearly factorable. I don't know. There's probably not a greatest common factor or any of our methods from before. But we can always try then and see, is it the difference of perfect cubes? So are each of these terms something to the third power? So 27 cubed could be written as 3x all cubed, right? Because the 3 cubed gets you the 27, the x cubed gets you x cubed, and then the 125 is actually 5 to the third power. Okay, so we have it written as something cubed minus something cubed. So our a and our b term are going to be 3x and then 5 respectively. Okay, so all I'm going to do now is I need to know the formula. Okay, and this is the formula for the difference of perfect cubes, and we'll talk about a way to kind of remember this in a second. But it's a cubed minus b cubed, so the formula says it's going to be, I'm just looking right here, a minus b, so 3x minus 5. Okay, then a squared, so here's the thing, a is 3x, right? 3x squared, when you square the whole thing, becomes 9x squared, plus a times b, 3x times 5 is 15x, and then plus b squared. Our b value is 5. 5 squared is 25. Okay, so there's the answer. That is factored. That's going to be factored all the way. And again, it was something we couldn't do without knowing these formulas. So one way to kind of remember these a little bit, let me erase this, because they are something you're going to need to kind of have down, and you know when to use them and how to use them and stuff like that. But if you take a look in each case, so when I say each case, there's the sum of perfect cubes and the difference of perfect cubes. The first factor in each is just the same. It's just the things are not cubed, right? So the first term is either a plus b or a minus b. Okay, but then notice in the second factor, okay, they both start with a squared. It's always an ab, but notice the sign change, okay? And I'm going to give you a little way, like I said, to kind of remember this. And then it's always plus b squared in both cases. So one little like memory aid that kind of works nicely is this SOAP thing. Let me write it out. Same, opposite, always plus. And what it means, so if you remember SOAP, right? S-O-A-P, it's telling you what the signs are. So if this is a plus, this one's going to be the same. The next sign will always be the opposite. And then in both cases, this is always a plus. Okay, so looking at the second formula, a cubed minus b cubed, it's a minus there, so it's going to start with the same, a minus, then the opposite, a plus, and then the last one's always plus. Okay, so just kind of work with those formulas or have them near you, especially at first when we're first doing these. But that's really the only way to factor these. I mean, unless you're like amazing at guessing and checking, but for the difference in sum of perfect cubes, there are a couple formulas here that we definitely need to know. All right, so let's review a couple older methods too, because these still are going to come up in the problems. So again, this is just factoring. We're not solving equations yet. We're going to use it to solve equations very soon, but just remember in the factoring methods. This one's a quadratic here, part A, so x squared plus 6x plus 8. So remember with those, we're just really looking for factors of 8 that are going to add up to this 6 here. Okay, so it's going to end up being x plus 4 times x plus 2. Okay, that should be something, again, we've done a lot earlier in the year. Part B here now, x cubed plus 6x squared plus 8x. That's one of the ones now, it does have a common factor. So if there's a factor in common to every term, always factor it out first. Okay, so we'll bring that x out and we'll be left with x squared plus 6x plus 8. Okay, it's still factorable because the one of the factors here is not fully factored. It's actually the exact same problem we did in the first example. So the x is still there, and then the leftover becomes x plus 4 and x plus 2. Okay, same reason again as part A. And then on part C, it's just a quadratic again. This one we had the a value of 2 here, so it's a little bit more complicated. So the method that I like to use then was doing that a times c little trick here. So the 2 times 6 is 12. And what we're going to do is break down 12 into factors that add up to 7. Okay, so to get 12, we could do 4 times 3. Okay, because those add up to the 7. And the trick is then go ahead and split up that middle term. Split up that 7x into a plus 4x and a plus 3x. Okay, and it doesn't matter if which order you do that in. You could do the 3x first, then the 4x. We did both orders earlier in the year, and they both worked. And then we do this grouping method where we say, all right, let's take a look at these two terms as their own little group, and then these two as their own little group. And we're going to do a little greatest common factor and hope things work out. So with the 2x squared plus 4x, the common factor there is 2x. And we would be left with, if we factor that out, an x plus 2. Okay, then we have the plus in the middle. With the 3x plus 6, they share a common factor of 3. And the leftover, if we divided the 3 out, would be x plus 2. Okay, now here's where we know we're in business, because each term now shares this common factor of x plus 2. So what we can do, just like before, when you have a common factor, x plus 2 is common, we can bring that out front. And then we just have the leftover stuff, the 2x plus 3. Okay, so that should be a review. It used some of the grouping method, and it also kind of showed the a times c little trick that we did on those quadratics. All right, so let's look at another example here. This one's definitely not a quadratic. This is a polynomial third degree. And a lot of times when they have 4 terms, okay, that grouping method that we kind of just saw in the last example is going to get the job done. Not all the time. You know, a lot of things are not factorable. Like tons of these are not factorable. But if they are, it's usually your easiest method. So with this one, since there's no common factor across the board, right, check that first. All 4 terms, there's nothing that goes into all 4. So we can just kind of move right along to our grouping process where we think of the first 2 terms as a little group and the second 2 as a group, and do it just like we did on the previous example. So let's take a look. With 5x cubed minus 8x squared, the biggest thing that goes into both is x squared. And we would be left with, if we factored out x squared, it would be 5x to the first and then minus 8. Okay, and in the other terms, so there's a minus sign there. So what goes into 20x and 32? Okay, the biggest thing that goes into both of those is just the number 4. Okay, and that would be left with the 5x to get the 20x. Since it's a plus here, I do need this to be a minus 8 because, again, we had that minus sign right there. So the minus 4 times the minus 8 does get me the plus 32. Okay, and that actually worked out nicely, right? Because now we notice they both have that common factor of 5x minus 8. So that means we can go ahead and factor that out front as the common factor. And the leftover stuff is the x squared minus 4. Okay, now let's be careful here. Let's not completely say we're done, because x squared minus 4 here is the difference of perfect squares, right? So the 5x minus 8 is a factor, but x squared minus 4 can be broken down into x plus 2 times x minus 2. Now we're completely factored all the way down to prime factors. Okay, here's one more that I kind of already worked out for you. If you want to practice one, maybe try not to look at the answer, but here's an example problem, and just it kind of walks you through the grouping steps, and you can see the steps there and verify that you're good on that if you want to take a minute and try that one out. Okay, and one other method that might come up and be usable here in solving these quadratics. So if you take a look at the term, the polynomial on the left, it's a fourth degree, right? It's x to the fourth plus x squared minus 20. Okay, all the methods that we have so far, the grouping method, grouping's really going to work when you have four terms generally. There's no common factor in there. It's not the sum or difference of perfect cubes like we saw at the beginning, so it's kind of a different thing. But it's what it's called, it's in quadratic form, where if you take a look at the one on the right, x squared plus x minus 20. Okay, let's factor that one out real quick and then come back, because this one over here should be doable. X squared plus, we can think of that as plus 1x. So factors of negative 20 that add up to positive 1. Okay, are going to be 5 and negative 4. So what I can do is just factor that right away into x plus 5 times x minus 4. And we are done, right, for a quadratic. Okay, so the problem on the left is very similar. Look at the coefficients, right? It's 1x to the fourth plus 1x squared minus 20. So the rule, or like the thing that's going on here, I guess, is you notice how this middle term, it's x to the first power. It's like half of the power of x squared. That follows suit here. X squared is half the power of x to the fourth. Okay, so what that means, what we can do, instead of just starting with x and x, okay, because we needed x squared over here, right? We need x to the fourth here. So we could do x squared and x squared. Okay, that would get us our x to the fourth. And then just follow the same exact thought process on the other one. Factors of negative 20 that add up to the 1 in the middle. Okay, and notice how the middle terms here, if we just check this by foiling it, it's not done yet, but if we check it real quick. So foiling it out, the x squared times x squared is the x to the fourth. Notice how the middle terms are going to be x squared terms, minus 4x squared plus 5x squared, and then the minus 20. And these do combine to become the correct middle term, right? They do become the plus 1x squared. So, like I said, it wasn't totally done, but just wanted to check it there that we're on the right track. And the only reason it's not totally done is just like the previous example, that x squared minus 4 is still factorable into the difference of perfect squares. I think it was the exact same numbers, x plus 2 and x minus 2. Okay? So just watch for that. Sometimes they show up. Again, it's called quadratic form because it's very, very much like a quadratic. It's just starting with a higher power of x. Okay, so those are some introductory factoring methods that will work on, again, some polynomials. Like quadratics, sometimes things are not factorable. And to solve quadratics, remember we had the quadratic formula to do that for things that were not factorable. Or even if they were, the quadratic formula worked. So with polynomials, when we're using factoring, again, this is going to be something to try. If it looks like it's clearly factorable, it's going to work. But there are other methods that we will be getting to in the next section. So that is that. We'll talk to you later.